Today, we're going to pull back the curtain on that invisible force that's all around us, electric charge. You know, the thing behind a sudden shock or a sock that just won't let go. We're going to look at the two main ways an ordinary object gets that surprising spark of power. I mean, we've all been there, right? You reach for a doorknob and zap, you get that little jolt. Or you pull laundry out of the dryer and have a sock that is just super attached to your sweater. Well, that's not some random fluke. That's physics, live and in person, and it's exactly what we're breaking down today. You know, at the very heart of all this static cling and all these little shocks is a really simple idea. It's all about the movement of these super tiny particles called electrons. When we say an object is charged, all it really means is that it's either gained a few extra electrons or lost some. That's it. That's the secret sauce. So here's how we're going to tackle this. We'll start with the absolute basics of electric charge. Then we'll dive into our first method, which is all about direct contact. After that, we'll get into the really cool one, a method that works from a distance. Then we'll put them head to head, and finally, talk about why this stuff actually matters in the real world. Okay, let's jump right into our first path to power, charging by contact. This is the one you're probably most familiar with, even if you don't know the name for it. And the key here is that it's all about direct physical touch. Now, the fancy scientific term for this is triboelectrocharging, but you know what? Let's just call it charging by rubbing. It's way simpler, and it's exactly what it sounds like. When you rub two different things together, that friction does more than just create a little heat. It's literally ripping electrons off of one surface and slapping them onto the other. Let's look at a super classic example. In step one, before anything happens, you've got a glass rod and a piece of silk. Both are neutral, totally balanced. But now look at step two. You start rubbing them together. That friction physically pulls those negative electrons off the glass and onto the silk. And the result? Well, in step three, the glass rod, having lost electrons, is now positively charged. And the silk, with its pile of extra electrons, is now negatively charged. It's a straight-up physical transfer. So that was the hands-on approach. But what if you could give something an electric charge without ever touching it? Well, that brings us to our second method, which I like to call a distant influence. This is where things get really interesting. Seriously, this is the mind-bending part. This method, called induction, lets you give an object a net charge with absolutely no physical contact. It honestly feels a little bit like magic, but I promise you, it's 100% pure physics. But to really get how induction works, we need to understand one crucial tool in our toolkit: grounding. Just think of grounding as an escape hatch for electrons. The Earth itself is like this enormous sponge that can soak up or spit out a nearly infinite number of electrons. So when we ground something, we're basically just opening a door for electrons to leave. Okay, so let's walk through this step by step. First, we bring a negatively charged rod near a neutral metal sphere. We don't touch it, just get close. Now look at step two. The negative rod pushes all the free electrons in the sphere as far away as they can get, to the other side. Now for the clever part, step three. We attach a ground wire to that far side. This gives all those crowded, repelled electrons their escape route. And poof, they flow away. And finally, and the order here is everything, we first cut the ground connection, trapping the positive charges that are left. Then we take the rod away. And what are we left with? A sphere that has a net positive charge, and we never touched it with the rod. So there we have it, two totally different ways, rubbing and induction, to get to the same end goal. Let's put them side by side so we can really see what makes them tick. Okay, here's the bottom line. Rubbing is basically a contact sport. It needs that friction to physically shuffle electrons from one thing to another, and you always end up with two oppositely charged objects. Induction, on the other hand, is all about influence from a distance. You just rearrange the charges and then give the ones you don't want an exit. And here's maybe the biggest difference. With induction, that original charged rod, it never loses its charge. It was just the catalyst, the influencer in the whole process. So you might be thinking, okay, cool science trick, but why does this actually matter? Well, it's way more than just a textbook concept. Understanding these principles is actually fundamental to how our modern world works. Think about a photocopier, for example. It uses static electricity to perfectly place toner on a page. Or think about industrial smokestacks using charged plates to pull pollution right out of the air. It's all about mastering and controlling this invisible force. All right, let's boil this all down. What are the big takeaways here? First, most stuff starts out neutral. Getting a charge is just about moving electrons around. You can do it with the brute force of rubbing, that's a direct transfer, or you can do it with the subtle, clever influence of induction. That's all about rearrangement. One needs contact, the other works from afar. Two totally different playbooks to get the same result. So I'll just leave you with this one last thought. We just saw how a charged object can literally reach out and influence another object without ever touching it. Kind of makes you wonder, doesn't it? What other invisible forces, like gravity or magnetism, are out there right now, constantly shaping and rearranging the world you're moving through every single day? Something to think about.